sure many of you have heard about the story on the news. It's been all over every news station for the last 24 hours. And this is the detection of gravitational waves. It's quite a fundamentally important discovery. It was predicted almost exactly 100 years ago. Almost exactly 100 years ago, this discovery was predicted and has been observed. So, briefly go over what happened. Here's the initial announcement video that I'm going to show you, for those of you who haven't seen it yet. This is the lead scientist from the NSF, which is the National Science Foundation, the American organization that runs all the kind of academic research that goes on in the US.
Ladies and gentlemen, we have detected gravitational waves. We did it. I am so pleased to be able to tell you that. So these gravitational waves were produced by two colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago. They were detected by Ligo, the Laser Interferometer Gravitational Wave Observatory. Ligo is the most precise measuring device ever built. Let me start with what we saw. So on September 14th, 2015, the two Ligo observatories in Hanford, Washington, and Livingston, Louisiana, recorded a signal nearly at the same time, nearly simultaneously, and the signal had a very specific characteristic of, as time went forward, the frequency went up. And what was amazing about this signal is that it's exactly what you would expect, what Einstein's theory of general relativity would predict for two big massive objects like black holes in spiraling and merging together. Now, it took us months of careful checking, rechecking, analysis, looking at every piece of data to make sure that what we saw was not something that wasn't a gravitational wave, but in fact it was a gravitational wave. And we've convinced ourselves that's the case, and we're here to announce that today. But I do want to say something else. This is not just about the detection of gravitational waves. That's the story today. But what's really exciting is what comes next. It's 400 years ago, Galileo turned a telescope to the sky and opened the era of modern observational astronomy.
So that was the initial announcement that was made yesterday, 3:30 p.m. Here's one of the observatories, this Ligo Observatory. It's basically a giant L shape, and they send laser beams down these two columns. And there's two of these experiments. This is the one in Livingston, and this is the one in Hanford. These are quite a long distance apart in the US. Here's where one of the observatories is, Hanford, and in Livingston. These are a long distance apart, 3,000 kilometers. It takes about 10 milliseconds for light to travel that distance. And their distance apart is important, because that's what allows them to calculate more statistics about these detections that they measure. And what do they actually look like? Well, here is the insides of the detectors, and here's why they're in this L shape that you see. Here's our laser beam, and here's a set of mirrors. Effectively, the laser beam gets split. Half of it bounces up here, and back down again, and half of it goes through and bounces up again. And so the two reflected beams meet down here. And it's called an interferometer because it looks at the difference between these two signals. Effectively, you've got these two sine waves, one coming up here and one coming across here, and these two sine waves interfere. And you get a resultant beam that can be measured down here. And any slight difference in the path length can be measured by the change or the phase shift in this, the wave that you get at the end. So here's the inside of the control center, they've called it, for the Livingston experiment. And these are all of the observations that they're taking. This is the control room for the Livingston interferometer. And here's the actual data that they got, as well as giving you the facts about it. Here's the actual graph plots that are in the paper that was published yesterday in the Physical Review Letters. And these are the two detectors. On the left is the one in Washington, and on the right is the one in Livingston, Louisiana. And these are the two signals. Until this point here, you've just got noise. There's a huge amount of noise in these signals. The reason being because the detection is such a minute adjustment in the frequency. Most of it is noise. But look what happened about 40 milliseconds in. get the sinusoidal oscillation in the amplitude or the phase of the wave. Right? And you get the one in Washington and the one in Louisiana, and they both detected exactly the same signal. But this one detected it shifted forward by a tiny amount of time, exactly the time it took for that wave to propagate from Hanford to Livingston. So that's why there's a very, very slight difference in where these waves occur. And the fact that they measured this to such a precise degree of accuracy. If you look closely on one of these graphs, you can see a grey curve in the background. This grey curve is what's predicted by Einstein's general relativity, and this red curve is what they've measured. Almost exactly, incredibly precise measurement of this oscillation. And in both cases, they've measured exactly the signal they expected. And this was a theory that was predicted 100 years ago, almost exactly to the day Einstein said that these waves should be produced. So this is the inside of one of the detectors. Here you have these waves travelling along these opposite paths, and of course they get recombined here, and they interfere with each other. And normally, because they're sent exactly 180 degrees out of phase, or pi degrees out of phase, you get an exactly perfect interference, which gives you almost no signal. But when one of them is shifted due to this squashing and stretching of space, you get this interference pattern. And so on the resultant measurement, you get this kind of this beam that you detected, which is exactly what you've got here. So why are these things actually produced? Well, here are two black holes colliding. And these are at the centre of the most massive galaxies. Our galaxy, the Milky Way, probably has one of these at the centre. And these are the results of millions of stars having collapsed under their own gravitational force. But when they get close to colliding, you get these huge fluctuations in the gravitational field. Gravity changes around the black hole. And you get these waves produced. You can see these waves oscillating out at the moment they collide. Now these black holes, in this animation I've only shown you them orbiting at quite a low speed. But these are actually orbiting at almost half the speed of light. 1.5 times 10 to the 8 meters per second. Incredibly fast. And you get these beautiful wave patterns that are produced by these powerful events. And these colliding black holes are the most powerful events that have ever occurred in the universe that we've seen so far. So these produce the largest signal. And you need this powerful event to produce a signal large enough that you can actually observe. It's never been seen before. And you get these waves that propagate through space. So these oscillations of the gravitational field propagate through space, and we've measured them at Earth. And of course, on one side of America, they measure the signal slightly before this wave gets to the other side of America, depending on which direction the waves came from. So this is what Einstein predicted. Einstein's theory of general relativity was almost exactly 100 years ago. And this is what he predicted. He said that this matter should cause these waves, but there's no way of detecting it back then. So Einstein was correct, and this is yet another another piece of evidence in favour of Einstein's general relativity. What an amazing discovery. So Einstein will be giggling to himself, I'm sure on that. So it's another proof of Einstein's theory of general relativity. Every test that this theory has undergone is passed with flying colours, and this is just another piece of evidence in favour of it. And it matches exactly to what he predicted 100 years ago. And the other thing is, as well as proving Einstein's general theory of relativity, this is the first ever detection of a black hole. This is the first ever measurement for the black hole to collide together and produce the signal. So we've effectively detected black holes for the first time. And these two black holes colliding is the most powerful way to produce these gravitational waves, these oscillations of space and time, produce these kind of weird oscillations that you see. And just as they collide, you get a peak in the signal. Because as they spiral in closer and closer together, the wave that you feel increases. If you were standing on a very precise set of scales when this wave came past, you would see your weight oscillate up and down by a very, very tiny amount, by a billionth of a billionth of a billionth of a gram. So it's a very, very tiny change that you see. So it's kind of a new era in astronomy. Now why is it a new era in astronomy? Well, until this point we've only ever observed electromagnetic radiation, so light effectively, radio waves, gamma rays, infrared, ultraviolet, UV, etc. But gravity waves is something completely different, and it's a new kind of observation that we can carry out that doesn't involve using light. Light is produced everywhere in the universe, but at a certain point, if we go far enough back in time, light wasn't free to propagate in the universe. But gravitational waves work. So this allows us to actually see behind the curtain that has obscured us so far. And so this kind of weird gravitational wave oscillation that you can measure allows us to trace back the universe even further than we have so far. The current limit that we can see is about 300,000 years after the Big Bang. But if we can measure these even more accurately, then we push this kind of window window back even further. So just to finish, this was Stephen Hawking interviewed yesterday.
Professor
on
Hawking,
BBC News.
how important is the detection of gravitational waves?
I would like to congratulate the Ligo team on their groundbreaking discovery. These results confirm several very important predictions of Einstein's theory of general relativity. It confirms the existence of gravitational waves directly. Until now, our observations of the universe have exploited light, radio waves, and other electromagnetic radiation. Gravitational waves provide a completely new way of looking at the universe. The ability to detect them has the potential to revolutionize astronomy. This discovery is the first detection of a black hole binary system and the first observation of black holes merging. The observed properties of this system is consistent with predictions about black holes that I made in 1970 here in Cambridge. The area of the final black hole is greater than the sum of the areas of the initial black holes, as predicted by my black hole area theorem. The properties of these black holes are also consistent with the black hole mode-air theorem, which says that they should be uniquely characterized by their mass and spin. Previous tests of general relativity have almost exclusively applied to weak gravitational fields. This discovery lets us test the predictions of general relativity when the gravitational field is strong and highly dynamical during the black hole merger. This discovery also presents a puzzle for astrophysicists. The mass of each of the black holes are larger than expected for those formed by the gravitational collapse of a star. So how did both of these black holes become so massive? I am sure the Ligo team are going to keep us busy with many further surprises.
So, as well as being an incredible discovery, really kind of groundbreaking historical discovery, this will almost certainly win the Nobel Prize in the year to come. It's an incredible discovery. It's such a precise detection. Probably one of the most precise detections that humans have ever made, the most precise device they've built. The fluctuations you get in the movement is about 1/10,000th the size of a proton. That's the movement that you get due to these gravitational waves. It's a tiny, tiny effect, and they've measured it using these laser interferometers. Quite an incredible discovery. As well as being the end of this, well, another confirmation of Einstein's general relativity, it also opens up a window on more things that can now be discovered. We can push back our observations of the very, very distant universe. We can map new areas of the galaxy. We can see these colliding black holes and the most energetic phenomena that occur in the universe. As well as being kind of the final word for general relativity, it's also starting an exciting new era.